Shall we start again?
Hello, Ayush, shall we start?
Yes, ma'am. We can. I hope the screen is visible.
Yes. Yeah, screen is visible. Can you
Yeah,
start?
yeah, we can. So, till now, am I audible? Am I audible?
Yes, yes, you are audible, but your volume is low.
Okay,
But
just
yeah.
now is it okay? Yeah. So in the morning session, so let me just give a from dataset. I'll be just selecting out the folder, and as explained in the earlier session too, this is how we'll obtain the image dataset. We can check for modality over here, the total number of slices contained in the dataset, and all the essential information are carried out in the decomp data text. Since this we have already learned, so we'll be just quickly clicking on finish. Once this is done, we can see the dataset in the three 2D views and one 3D view as we have discussed it multiple times. Now, coming on to auto segmentation. So, first of all, we know that generally from the sample data set that we provide. Let me take another example. That's the recent case I am working on. It's a live patient data set uh, shared by a company to do the segmentation. So I'll just open that. Yeah. It takes some amount of time when we have a large number of series present in dataset. Yeah, so this example is also one such great example in which we can see how different set of data series can affect our result. So whenever we are obtaining a TICOM city directly from hospital, we may get data in this type. So it is carrying around 10 to 12 series of the data set corresponding to the different views, corresponding to different thickness, and depending on our use case to use case, we can choose any of the series. For example, in this particular set, we can see there is a clear visualization of pelvis, so the segmentation can be done quite easily. Over here, we have a great visualization of spine, so this can be considered a good example to segment out the spine. This particular part has good visualization of kidney and other soft tissue. So soft tissue identification will never be an issue. So depending on our use case to use case, we can use the particular feature. This one specifically focused on the renal. So the particular kidney part is of the top priority over here. So we can do easy segmentation. We can also visualize the result by zooming in the data set. Now, what I was discussing is the auto segmentation feature. So once we have loaded one particular sample, we'll just click on finish, and it may take some amount of time, around 1 minute, when we have a large data set, and it is comparatively large data set as we have operated before. So once we have generated the data set, we can see the data set memory size is around 64 MB. Now, whenever we will be obtaining a CT scan data, it may often contain a region larger than the hip or pelvis that we need to focus on. And since I am taking an example of pelvis, that's why my prior focus should be on the pelvis region. So the speed of tool is generally influenced by the volume that is contained in the region of interest. Right now, since it is around 64 MB, so it will use high computational power to do the splitting, to do the segmentation. But here comes the magic part. Our HipCity automated segmentation tool can select the region of interest, or we can also specify it manually. So whenever we will be clicking on this hip revision city, we shall be focusing on multiple parts. So you can see over here, we have the left hip, we have the right hip, then we have the left femur, we have the right femur. We are also provided with the sacrum part. Apart from that, we are also provided with three other options. One is create landmarks, that plays a very crucial role. All the plus marking that you can see are the field landmarking points. So when we will be segmenting out the data set, it will identify the important regions. So for example, if we are clicking over here, so we will be getting the left femoral head and right femoral head accordingly. Also, there is one more feature in which we can keep all those small bone fragments. So whenever we are dealing with any trauma data set or a fracture data set, it contains small pieces of bone. And to segment such cases is quite difficult, as software might also interpret as any noises, and it will automatically try to remove the particular noises. So if we will be clicking on this keep all bone fragments, so even if there are small pieces, that can be stored too, and we won't be facing any problem in dealing out the same. Now comes the next part is having the output of femur cancellous bone as separate. Because the earlier segmentation methods that we used to have, it used to solidify the cancellous bone part, and it is good for 3D printing. But if we are not doing 3D printing, if we are using it for research, for doing any finite element analysis, for doing any CFD analysis, not for CFD analysis for bone, but if we are doing any nerve based analysis to export out a step or IGS file, in that case it may cause us a problem. So now we are also supported by this output of femur cancellous bone as a separate part. Once we click over this, we just need to click on apply. And now, since our region of interest was this specific part, so we selected out all region. And furthermore, if we needed to segment out any specific region, for example, if a particular patient is having an acetabular fracture, so what we can do is we can just select out the right hip part followed by the uh, right femur, and it will do the segmentation accordingly. Currently, the landmarks that are available are for proximal femur right and left, where we can mark the lesser trochanter, then greater trochanter, and femur head center. Similarly, with right and left hip, we can mark the pubic tubercle, then anterior superior iliac spine and posterior superior iliac spine. And for the sacrum, we can mark the corpus. So these are all the plus markings that I just explained. We can also learn about these particular markings and the auto segmentation tool from the health guide. But just to give an overview, I'm explaining this part. Meanwhile, we have seen that once the segmentation is done, it had taken around 1.5 minutes to complete out the segmentation. The current system I am using is accompanied by a GPU, so I am using on a remote laptop system with a configuration of Wi-Fi 12th generation and a GPU of RTX 4060. So the computation time is quite faster, and we get the output result quite in a very quick time. Once it is done, we are also accompanied by a summary tab. So whenever we will be using any automated segmentation feature, we will be accompanied by the summary tab, which will tell us whether the particular region that are present. So what we have used is a HIP revision CT. Let me tell a brief about in which cases this particular tool is used for the most of the cases. So the cases in which there was some problem after operation was conducted and patient is facing issues with the existing implants, or if he has faced any trauma like a fractured part, or even if there is a wear and tear of implant over a period of time and he needs to have a replacement surgery from the existing implant to a new implant. This feature plays a crucial role. As when we are segmenting out any titanium part from a bone part, it may cause some problem because generally the titanium will have the grayscale range between 2700 to 3071. This is the general titanium grayscale range that we can see on any data set, and it varies accordingly. And the bone region also lies between uh, around 150 to 3000. So there is some range around to 2700 to 3000 grayscale value units, which overlaps both titanium and the particular bone part that we would be working on. So to segment that, this auto segmentation plays a crucial role. Also, it tells us what all are the key identification points that it has identified. And since this being a actual patient data set, so we can have a greater knowledge about the uh, anatomy. Also, whenever we have generated out the segmentation, we can see how the output has been generated. We can overlap it with the volume rendering, and we can just cross verify the specific parts that are required for our workflow. For example, if we are working on a hip right, we can just right click over here, we can isolate it, and we will be just working on our right hip part. But there might be still an issue that it is not looking very accurate, or it requires some sort of smoothing. So what we can do in such cases is we can go in the image processing section. In the smoothing filter, we can use a recursive Gaussian or a smart mask smoothing. Let me use the smart mask smoothing. I'll take number of iterations that how many process we need to repeat over this particular grayscale to smooth out the part. So let me take the process as 5. I'll just apply the smoothing. Since the active mask was selected as a hip right, so we have the target mask accordingly. Once this is done, we have smoothed out the surface. We can check out the smoothened surface from here, and then we move on to our next part of bringing any implant. But before that, there is one more feature that I need to show. So earlier on, we used to just have this orthopedic part and the cardiovascular part to do the segmentation, segment out the anatomy. But now we are also supported by an external model. So what is this external model? External model is nothing but whatever segmentation algorithm that we have developed on our own, and we need to cross verify its accuracy. So that can be done in a very easy and efficient way. How can we do that? So just we need to do is we can go over here in the installation folder, and yesterday we have shown that how we can do the environment installation. So we need to go in the program file. Inside that there is a folder synopsis, simpleware software, and in the external models option, we can install the particular any external model that is required. For example, if we need to install the total segmenter, we just need to right click, run as administrator, and it will start the process. Since this all are already completed in my system, so I don't require it. But we can install the particular bundle. We can check what are the templates that are available, what are the scripts that are available. So if we are familiar with the Python scripting, we can edit the particular part out and cross verify the region and do the segmentation accordingly. Coming back to this particular part and why this particular thing is important, because sometimes it may happen that we need to segment out certain anatomy that is not present in my existing orthopedic automated segmentation, and we might need to rely on this external models option. For example, if we are doing a liver vasculature segmentation, or for example a kidney segmentation, so you can see there is no option of soft tissues as much, just the option that is available for soft tissues for heart CT and heart valve analysis. Also, for other minute bones that are present, the rib cages, we don't have the option for rib cage over here, but we do have the option in the external models. Let me show that. We just need to click on the external model. Here it will tell us what are the total possible outcomes that we can segment out the particular parts for. We first need to uncheck all and then we can select out our specific parts that are required. For example, if I need to identify all the particular ribs, so I'll just click on all the rib region, and it will take some amount of time to process because the generally the external model is a bit slower than its simpleware's proprietary tool to do the segmentation, but it does fair job while doing the segmentation. Also, if we need to highlight some other regions like stomach segmentation, kidney segmentation, that is vasculature segmentation or any soft tissue segmentation, which will covered on the day fourth session, we can do that just to show how if the part is not available in this particular orthopedics, we can still do the automated segmentation. I'll click on apply. Before applying, let me bring it in a separate segmentation folder so I can segregate the particular parts out. To do that, I just need to right click over the object section, and that we will get an option of new folder. When we will be clicking on this new folder, we can just type hip auto segmentation. So hip AS. And now, whatever result that we have obtained from hip automated segmentation feature, we can just drag and drop it over here. And this way we have a simplified view. We will not be having unnecessary objects over here. And we can just filter that out. Also, if we need to toggle all the particular visibility off, so I can just click over here and we can work accordingly. So let me just unhide it. And if, for example, I need to visualize the particular structure, what I need to do is I just need to just right click over here, toggle visibility, and it will open the surface for us. And we can highlight each and every region. And similarly, in a single click operation, we can discontinue that. Now, coming back to the external model option and the auto segmentation that is available for external model, we have selected a total segmenter. We will click on apply, clicking on yes, and the process will start. This process generally takes around 3 to 4 minutes to segment out the particular part. But when the segmentation is completed, it might be not that proper. So we need to still use separate operations. So one might ask what sort of operation we can use. So whenever we are working with such tools, what we can do is we can use local surface correction to correct out the surface, followed by a smart mass smoothing or a recursive Gaussian. And ultimately, the particular type of surface that we would be getting would be a high quality surface, and we can definitely rely on the segmentation quality for the same. One more feature that it offers is whenever we are doing any automated segmentation, for example, for hip, and we have also done the same automated same using manual segmentation, and we need to check the segmentation accuracy of the manual segmentation as compared to auto segmentation. So we have a tool in measurements known as mass similarity calculator, which helps us to do the same. I'll show the mass similarity calculator for now, but other measurement tools I'll try to cover out in tomorrow's session. So let the particular process be completed. Meanwhile, let me take this particular example only, and again I'll apply an auto segmentation. Once I have applied this auto segmentation, so let this process also be completed in another window. Meanwhile, these two processes are working. Why I have done this? Because I need to show how the particular mass similarity calculator works. We'll be just opening out auto segmentation tab. that is the proprietary tool over here, and then I'll be just carrying out a quick semi-automated segmentation using the manual approach, that is the threshold-based approach. Also, yesterday we have shown that there are various presets that we can directly select out to segment out anatomy. We have a preset value set for bones from 230 to 3070 or 3000, and then we have for muscle 0 to 140. For skin we have in negative minus 729 to minus 129, and then we have for the air region that is present to segment out the lung region. There are also other segmentation tools that play a crucial role while we are working on any specific important project, which is much more focused on tumor cases. Because what is our ultimate aim is to do the research on the parts that are most difficult to work on. And these are basically the tumor parts, either oncology tumor or the soft tissue tumor that we need to identify and do the segmentation for. Meanwhile, the auto segmentation is completed. Now I'll also carry out I'll just quickly sum it up in a folder, writing as a step, selecting the particular parts, and then dragging and dropping over here. Now, coming back to the manual segmentation that we generally follow. So we have a threshold-based approach. We select out a grayscale range, and once our grayscale range has been selected, we can just click this option to quickly do a segmentation. Once this segmentation is completed, I'll just generate a fast preview. Now, to showcase on a smaller part, uh, let me do the splitting. Splitting region, as told in last session, we need to toggle live 3D preview, and then we can split out this particular parts. For example, if I am doing the left tip marking, I can just mark the outer region. I am doing a quick marking, so sorry if the results are not that proper. But if we take time and into consideration, we can do a proper marking, and it won't take around more than 3 to 4 minutes to mark a proper boundary for the same. So similarly, we will mark it up here. You can see there are some wrong markings for the hip right that is already done. So I'll just remove that from here and just delete the selected, and then I'll add a region, rename it hip right. Once it is done, I'll just mark the boundaries again. Similarly, we will do over here. So we have just selected the parts over which we need to do and carry out the segmentation for. Now I'll be just selecting a left femur like this and followed by a right femur. So this is just a quick way how to segment. I don't recommend to be that fast, but if we are marking it thoroughly and if we have a proper marking, we can do a great segmentation from the same. Once we have done this, we'll just click on apply. Yeah, I think it has done a decent job while doing the segmentation. We'll just be deleting the region. And now I need to show how the mass similarity calculator works. So let me isolate this femur right part. I'll apply certain operations to further smooth out the part, to solidify the bone, so that we can have an accurate representation of what we are having in the automated segmentation. So I'll quickly solidify the particular bone part, and the bone filling process also takes around 1 to 2 minutes for it to be completed. Once it is done, we'll apply a local surface correction, and then we will apply a smooth filter to smooth out the anatomy. Or even if just to show a particular feature, I can also we can see it has solidified the bone part. Now we can just use a recursive Gaussian filter. 1.2 would be a good value for this data set, and this particular value, once we get used to the software, we will be getting to know better about how the particular value varies, in which case what value can be taken. It all depends on the experience with the tool. Now we have developed a manual segmentation. We have also developed a fully automated segmentation of the same. So, sorry, let me change the color. you can see that now to check for the accuracy, we have two approaches. First is either we can overlap with the volume rendering and it is looking okay. But since our main concern was how accurate is the auto segmentation or how accurate is our manual segmentation. So we go over in the measurement tab and here we select a mass similarity calculator. Now we will select the particular mask for which we need to do the comparison for. So taking the input A as femur right that was generated using the auto segmentation and then femur right 2 that was generated using the manual segmentation. We'll just click on calculate and it tells us the dice score being 0.9595. That is the particular mask are 95.95% similar and we can check the accuracy simultaneously. And the value around 0.95 above 0.95 is considered a great value while we are doing or generating any segmentation algorithm. So even if we have developed our own set of segmentation algorithm and to cross verify its result, we can use this type of approach. Now coming back, I think it has done the automated segmentation using this external models over here since we had selected the rib part. Now I'll just quickly generate a fast preview. So this is the advantage that I was showcasing. So here we have got a great mask of rips to be generated. One might still say that there are some surface corrections that are required. I completely agree with that. So to do that, what we can do is we can either apply some smoothing procedures to show that we will be just going to a smoothing filter and recursive caution, taking any rib left, for example, that is I think so this particular blue one, clicking on apply. Yeah, so it was this particular one. Let me take another one that is visible clearly. So it is rib left one, this is this one. Apply the operation performing a fast smoothing and it has done some sort of smoothing but still the result is not that clear. So what I'll do is I'll instead go to the local surface correction, taking for example this particular version. Once rib left 10 is taken, I'll apply the operation again. Once it is done, we can increase the Gaussian value over here around 2 to smooth out a particular part. And we can see that it has smoothened out this, but still the parts are missing, some parts get disconnected. So to correct this particular files, we are still supported by another feature. So we can go to the specific point, so left button in my mouse followed by the keystroke. We can go to the specific point and then followed by a smart paint tool. We can again brush it up or else I can show a better approach. We can go in the background flood fill. Here we can select a seed point, selecting a value between 50 to 50, operation as merged. And now whenever we will be clicking on this operation, it will slowly add up the different regions that are being present. So for orthopedic, we can take a value between 50 to 100. For soft tissues, we generally keep it around 5 to 10 units so that it automatically solidifies the region and add up the particular region for us. And you can see whenever I am marking a particular point, it is visible in the 3D view, but still the mask is not getting updated. So to update the mask from time to time, what I need to do is I just need to click on this generate a fast view and we can see how we can solidify the different regions. So this is one such great approach while we are working with this auto segmentation. Coming on to this auto segmentation again, let me showcase uh, some other data set cases. So we do have an EMRI case that I think was showed in the morning session. Similarly, a knee case was also shown. But let me take up an example of a fractured mandible. Why I'm taking that example is because we will see the capabilities that the software has in terms of auto segmentation. And auto segmentation is one such key feature that distinguishes Simpleware from its competitor software that are available in market because it's one of the proprietary tools that the team has worked quite hard to just develop the particular part for us. So just selecting the particular fractured mandible chip, clicking on auto segmentation, Here we will be selecting a craniomaxillofacial CT scan. We will be highlighting out the region, clicking on keep all bone fragments and split teeth. So it will do a detailed auto segmentation for us. CMF CT scans generally take 2 to 3 minutes to be computed. Also, it depends from scan to scan. So if it's a 3D CT scan, it might take a little more time. Just give me a second. Yeah, sorry for the interruption. So this being a CMF CT scan, it takes some a greater amount of time as compared to a normal pelvis scan, or knee scan, ankle scan. The smaller the data set, the faster it would compute, and it's a slightly larger data set that we are operating on. Also, this has a fractured part, so it is slightly difficult to identify. So what we can see is it has identified the cranial cavity followed by the mandibular nerve. So any nerve region can also get identified. Also, all the airways, all the ear canals are identified in a single view operation, eyeballs, mandibular nerves. So we can directly check out if we are having a full city, so we can also highlight the cranial cavity that is present, and we can also select out the parts. And not just that, all the particular molars lower, then molars upper, incisors, canines, all the particular parts are being identified. This we can do, and this is a fractured data set. So uh, these are the cases which are the most complex, that comes into the complex category to deal up with. So we can do easy segmentation for such cases too. Now, coming on to the next part is the finite element modeling, the nerves modeling that I was discussing in the yesterday's session, as well as the discussion was done in the morning session too. So, to do a model generation, what we require is our first initial requirement is to do the segmentation. And I hope by now everyone is familiar with the concept of segmentation, how to segment out anatomy, how to work on the specific part. Now, our main task resolves around generating of implant in any software, and then bringing out that implant and doing the pre-positioning and positioning with the image segmentation software so that we can have the best output generated. Also, we might also require a finite element model to be generated. So if I go step by step, some part of finite element modeling might not get completed today, but I'll still cover that out in the tomorrow's session. So we can have a brief about the finite element modeling in this session, and I shall be showcasing in detail how we are going to work in the finite element modeling, what are the modifications and changes that can be done. Now, coming back to the implant positioning and how the particular implant tool works in simple way. So it's very easy process, to be honest, to work with implants in simple way. We have dedicated tabs and we have a design link module. Since many of the particular participants are from mechanical background, so they must be familiar with SolidWorks software. To link up Simpleware with SolidWorks, it's a very good tool because we can directly click on import and we can open an SLD part or SLDSM file from here. So that is SolidWorks assembly file and SolidWorks part file can be bringing, and we can directly link up both the tools. So whatever modifications that we will be doing in SolidWorks will be live visualized in Simpleware, and whatever modifications we will be doing in Simpleware will be live visualized in SolidWorks. We will be we need not to do again and again import and export. We just need to link the software once, and the tool will work in background. Whatever modifications are required, we can do the same. Now, coming back to the import surface. For example, one might ask if we don't have SolidWorks, we are having another tool such as a Freeform or any CAD designing software that Blender that they are using to develop any STL file or CAD file. How we can import the surface in that case? So that too is covered. We have the import surface option in which we have the STL, serial lithography file, PLY file, the IGS file, step file. IGS and STEP are advanced CAD formats that are available that we can directly import. That is initial graphic exchange specification and the step file format that we generally have. So these are the two formats that we can take the data from anytime. So all the particular designing tools are compatible with Simpleware. We are quite familiar with the file. The support is quite good. Whenever we will be importing out any STL file, we need to select out the folder that is containing the STL file. Once that is selected, we just need to double click over there and a particular pop-up window will open which tells us from which folder the particular file is taken from. We are also given advanced scaling option. Either we can set the scaling custom, or if we need to change the scaling from meters to millimeters, from inches to millimeter, centimeter to millimeter, we can do any approach and we can bring that into millimeter size. Also, if we are having multiple STL files, for example, if we are having a femur stem and we need to divide the femur stem into stem and the head part. So we can also click on this import individual connected surface as separate objects and it will split up the particular part that we are working on. And not just that, whatever STL file information, the total number of polygon points, the total number of points that the particular surface is having, the whether the particular file is watertight or not, we can check from here. And if it is not, what we can do is we can click on the fix up the surface, so it will identify the defect region. It will highlight all point, and we can go to the specific point to correct out the error that is present. Also, if any self intersection is present, that too can be corrected using this fix module, and we can update the surface. What is the physical extent, the actual dimensions of the object can be visualized from here. So it's a 5 centimeter, 5.6 centimeter cross 5.6 centimeter cross 2.6 centimeter of object, the of acetobler cab implant. Once it is done, we just need to click on import the dataset and it will bring the particular implant in our viewpoint. But still, we are missing one point that it is not in our working view. Why we highlight this working view is whenever we are dealing with such objects, we first need to bring out in the existing working view. To do that, we are given with one more option. So we need to go in the transforms section in the surface tool. Here we will click on the zero position. Now, since in the surface section, only one surface is active, that is acetobular cap cup implant. So what we will do is we have already selected the object. We just need to click on apply and it does the magic. It brings the particular implant into the origin position, that is 0 cross 0 comma 0 comma 0, that is corresponding to XYZ coordinates of the following implant. Once it has brought down the particular implant at the origin, we need to click on the register data set, and in the register data set, we need to update the particular parts that we need to work on. So for example, if I'm working on a hip right, I'll just select it from here, and then I'll also select the acetobular cap surface that I'm working. I'll select both the parts that I need to do the particular positioning and orientation. Once that is done, we need to click the registration method as automatic, followed by the fixed TICOM data set as a hip right. So once it is selected, we will be getting the particular position in the following view, and we in the moving data set we can take the acetobular cup implant. So we have two options: either we can mark up the particular boundaries in this particular 2D view, or we can enable the 3D mode, which is the most easiest mode to mark up the particular region. So for example, acetobular cap should be somewhere around here. So what we need to do is we need to click on the registered region. We need to click on the triangular selection. Once that is selected, we will be selecting a brush. Now we need to increase the brush size by a little amount, and then we can mark up the region over which we need to bring the acetobular cup implant pot. Similarly, this is a pelvis example that we are considering right now. Even if there's any other STL file, and we need to do the positioning of any STL file from one data set to another, that can be done. Even if any CT needs to be overlapped with the MRI, that too can be done from the same method, that is the registered data set. Now, since we have selected this acetobular cup, If we are having a proper STL file, so we can sorry, so we can click on this brush. Then we can need to click on this grow selection by threshold. So even if we are marking a slight region, it will mark up the whole boundary till the curvature. Just give me a second. Yeah, so once it is done, we just need to click on update and it will bring our acetobular cab implant nearby to the hip position. Once we do this, we can again cross verify it. We can change the planes if required over here in the viewing section, or we can correct out the same. But if we are okay, we can just click on enter and it will bring the particular parts out. And since we have shifted the region, what we can do is we can go over in the position and orientation. We can select out the mode as 3D and we can directly bring the particular file over here. So let me show a better way to do the same. So we have brought the particular file. We can do the particular dimensional changes, the orientation changes. Over here, we can do a proper positioning. And now, what else we can do is, we can go into 2D view. In the 2D view, we have got the particular hip region. And once we have got the particular hip region, we will be particularly marking the acetobular cap accordingly in the 2D view. So we will be selecting the 2D view. We'll be checking where is our acetobular cap implant as active surface. Bring it in our view. Yeah. So let me recorrect this particular surface. It got a little glitch. So since I also have the auto segmentation done for this part, let me toggle its visibility off, taking the same right sample. Now working on the surface tools, bringing in the implant, tubular cap, clicking on import, and then doing the position and orientation. So either I can do in 2D. So to do it in 2D, what we need to do is we can directly shift up the point to the exit region that we are working on. We can zoom in the part and then we can do the particular position over here. So we can get the most precise value to the nearest decimal possible. Once this is done, we can check the output over here and furthermore, if any correction is required, either we can increase the dimensions from here, we can change the positions from here in the decimals of millimeter, or we can just do the marking somewhere around here. So like this, we can do the particular position, and once the positioning is done, you can click on apply, and it has applied the particular acetobular cap implant according to the pelvic surface. Now, this is just one part that we have brought in the particular implant. We have done the positioning. Now, one more feature that we have is if we are having any STL file and we need to check for any errors that are being present. So for that, let me convert the existing hip right mask into a surface. Just generate a fast view. So we need to click in the dataset conversion. We need to select the mask to surface. Here we need to select the particular part that we need to convert out into a surface from the existing mask. Once that is done, now you can see there are two different surfaces. One is this hip right surface that it has developed and another one being the acetobular cab implant that we have brought in. Why we have worked on the surfaces when we are working with any 3D printing, there might also be a need to reduce the weight of the particular part. To do that, we go in the internal structure wizard. Here we can select different types of unit cells. So for example, if we are selecting a cylinder grid, a 3 cross 3 cross 3 dimensional, we can see how the internal structure would look like. If we need to develop a porous structure, so we can select a particular porous structure over here, just clicking on finish, and we will have a separate structure. We can see how the internal structure would look. So what it will do is it will create a hollow structure with the following internal attacks. This ultimately increases the tensile strength of the object. Also, the distortions, or if when we are doing the 3D printing, so the defects are generally less produced when we have a good internal lattice structure. So this way we can also develop a internal lattice structure. We just need to select out the STL file or surface file that we are working, clicking on next, selecting the particular file. We can see the exact computer aided design dimensions, the XYZ values, and then we can also set out the coarseness of the internal structure that is required, the thickness that is required, or any other part that we can generally miss off. Also, there is one more feature. For example, if I'm working on this part and this part, let me do further modifications. So let me do the controlling of particular cap. It is done. Yeah. So I think it's proper now. Now, what if I require a connector between these two particular surface? To do that, either we can do two sets of operations. We can combine this surface as one using the Boolean operations. So we can use the general Boolean operation. We can apply a union feature. Let us select a new surface object, selecting a acetabular cab implant in the hip right. So here we'll select the acetabular cab implant, clicking on apply. So you might see there is an error. So why this error occurred is whenever we are doing the particular Boolean operation, we need to take one thing into consideration. There shouldn't be any gap. The particular surface should stick with one another. To correct it out, we can again shift up, we can do the particular sticking as one, and then we can apply for the operation. Also, there are certain advanced tools that we can further work on. So there is one clip tool. Clip tool is very essential while we are working with the 3D printing because it offers us two sets of operation. Either we can select out any plane. Taking this example, we can segregate these two particular parts out, or else we have an option of partitioning also. So if we need to have two separate surfaces from the existing single surface, we can do that. Here, no capping will keep us an open face, and if we select a quick triangulation, so it will close the particular surface face directly for us. Once it is done, we just need to click on apply, and we can see it has closed out the surface for us, but it has done the splitting task. So we can use the advanced clipping option or partitioning option, and we can divide surface into any parts. Apart from it, if we need to decimate the surface, we can work accordingly. Once it is done, we can also check the surface quality, and we can check for the decimation strength. Similarly, if we need to fill any holes, if there are present, we can do that. If we need to hollow out the structure, we can complete that too. Removing of triangles can be done, smoothing of the surface can be done. So even if we are working with any STL file, CAD file, we are provided with multiple set of options to carry out that too. So this is just a general overview about the surface tools, and it is a very detailed tool to be honest, because each and every tool that is present over here has a different set of functionality. For example, a check and fix. Whenever we will be using a check and fix, we will be getting what all defects are present in the existing surface that we are working. So I will just select the active part. So in the active part that is selected is the hip right. It doesn't has any error. But I'll select this particular hip right from mask, that is the other part before the partition, the blue region. It is having certain defects. To check and fix the particular defects, we can go into check and fix column. Once we go in the check and fix column, we can also see the exact point corresponding to which the error is there. So whenever we will click on the particular feature, it will tell us corresponding to this component, this is the error is occurring. We can check any at what point the self intersections are present. at what point the surface error is present or the hole is present. So either we can go manually and fix that, fill up the hole, or the software will detect that automatically and do the task for us. Once it is done, if we need to basically clear out all the surface errors that are present in a glance, we just need to click on this fix surface option. Once we will do, it has removed all the surfaces and then we are ready to go for our 3D printing. We can directly do the exporting of the particular part for 3D printing. We can go in the 3D printing option. We can export scene to disk and then we can select out the file for 3MF, STL, OBJ, PLY, 3D PDF, and also even if we need to export the particular file for virtual reality, that too can be carried out. Now, the 3D printing tool tab is itself a full option that we can check. And this part I'll cover out detail in the tomorrow's session, where we shall be focusing on each and every tool that is present for 3D printing, additive manufacturing users. So, and the measurement also will be told in detail about each and every feature, the counter visualization, fall thickness tool, center line network tool, and also report generation. We will be also covering the material reverse engineering part and the finite element modeling in detail in tomorrow's session. But just to show how we can generate any finite element model, of, so I'll just give a quick brief for the same. For example, we are taking this hip right and we are also taking this femur right. So let me take this femur right. I have taken these two examples because it's the perfect example to show how to generate a finite element model for the same. I'll be just selecting these two particular files. To do that, we can just click left click over hip right and then pressing the control key, we can also click on the femur right. So it will only select these two particular parts. Then we will be moving on to the model section. Yes, sir. Multi-material modeling will also be covered in tomorrow's session in detail. We shall be focusing on how to assign the material properties as well as to generate how any surface structure for doing the 3D printing. All will be covered in tomorrow's section. So all the reverse engineering part, multi-scale modeling, and multi-material modeling will also be covered. I'm just giving a brief of how to just do the export quick model creation in a few, but we will cover this in detail because it's a big topic, and I think we should give a dedicated session for it. So tomorrow in tomorrow's morning section, the lecture would be semi-divided into both the live demonstration and the presentation part for the finite element modeling. So coming back to the finite element modeling, whenever we will develop a finite element model, we will be getting an option of model configuration. We can set out the model tab over here, whichever model type is required. Since it is having support of multiple export types, we can select from here. We can select a Vegas file, Adena, ANSYS workbench, COM. So, for example, let us select an ANSYS file. If we are developing an ANSYS file, we have select since we have selected the two different masks, being the femur right and the hip right. We can set the coarseness level accordingly. One can have a higher fineness and another can have a